So, yeah, evolutionary algorithms. Thank you for the kind introduction. My name is Manuel Ernst. I'm from Erlangen, that's in Franconia. I'm a developer and technical lead at Musikhaus Thomann. Musikhaus Thomann is an online retailer for musical instruments, and I'm working at the online store there. I'm Serious Manuel at GitHub and Serious Manuel as well at Twitter. So the topic is evolution, and I think most of you probably know that guy. That's of course Charles Darwin, and most of you people would probably know also the term survival of the fittest. Survival of the fittest describes how a certain individual is surviving, or is more probable to survive if it is good adapted to a certain environment. Also, it describes how an individual is more likely to die or get wiped out if it is not so good adapted to its environment. The theory of evolution describes how genes and properties of parents are inherited by their children or their offspring, and and it also describes how overall population is improving by inheriting genes and by the fact that least adapted individuals are wiped out from the gene pool. So to explain it a little bit better, I have created a fictional world that's loosely inspired by the novel Flatland. Maybe some of you have heard of that. It's a two-dimensional world and it's red. Not so spectacular. But CIRCLEWORLD is inhabited by circles, hence the name. And circles have two specific properties. They have a color and they have a radius. You see there are red circles and blue and yellow and green and small and big and medium-sized circles. And there are some happy folks. From time to time, when two circles like each other very much, they produce offspring. And when they are reproducing, the genes of two circles are used in the offspring. So in that example, the big green dot, that's the child, has inherited the size of the red circle and the color of the green circle. Another possible child would be that small red one. It has the color of the big circle and the size of the green circle, but it's of course more likely that a child looks like this. It's yellowish and small, medium-ish. It's of course a mixture of the both colors, green and red, and of the radiuses. Sadly, CIRCLEWORLD is not only inhabited by circles, it's also inhabited by the predators' triangles. And triangles do eat circles. When this poor fella has been eaten, of course, the other members of the population say, okay, we have to reproduce to keep up our overall population, and they're reproducing into this from this brown one and blue-grayish one into that small gray individual. Since we're living on a red circle world, the environment is very good, or a circle is very good adapted to the environment if it's red, because when it's red, it can hide from a predator. And if it's not too small, but not too big, it also is able to defend itself and to run from a predator, e.g. the triangles. So with these criterions, we have the possibility to rate our individuals from the population. I'm doing this by using these nice Facebook thumbs. And as you can see here in the chart, the big red one in the left upper corner is far more fitted to the environment than, for example, the brownish, grayish one. It has two thumbs down, and the purple one has one thumb up because it's big, but it's not so red. And the reason why the gray one is now getting eaten, is because it's not so good adapted to its environment. It can't hide as good as the red one, and it can't run or defend itself as good as the big ones. That's about the general idea of the evolutionary principles. All in all, we have some terms, and I want to iterate onto them a little bit more. First, the population, that's all of the combined circles together, the green one, the red, and so on. The term recombination describes how two circles are combined together to form a new offspring. Here in that example, the red and the green one form the yellow one. Then we have the term mutation. That's a new thing. And mutation is caused, for example, by nuclear radiation, and it causes some of the genes to slightly differ. So that red circle is morphed into a lighter red and into a little bigger radius. We have the term selection, and selection means a triangle counts and eats a circle. And normally it is, of course, a circle that is not so good adapted to its environment, so it means usually it's not as red as the others. The term fitness, that's our Facebook thumb thing. So the big red one is, of course, very good adapted, fitted for its environment, while the green small one isn't as good. It has two thumbs down. So we have some building blocks, and now we can put them together into an algorithm. We're starting by create a initial starting population that is as random and as arbitrary as possible. We have a while loop that simply runs as long as the program runs. On every step, we first choose two or more parents. We take those two parents and combine them into a new child. That's the recombination step we just saw. Then we mutate that offspring. And mutation means let's add something here and put something away here. We then rate the offspring, so we put our Facebook thumbs on that thing. And we add the offspring to the population. And then we are checking if the offspring is actually fit enough for the task it's facing. And if not, it's immediately removed. If it is actually quite fit or fitter as others, then the least fit individual is removed by getting eaten by a triangle, for example. If we have a certain termination criterion, we are simply exiting the loop. So I've put that together into a little implementation. That is our circle world and our circles, of course, the red background. And in the left upper corner, you see the individual that is best fitted. And the right bottom corner, you see the example that is the individual that is least fitted. So it's bluish, small, and so fitness is bad. And in the box on the right side, you see the parents that are chosen. When I'm going to start that algorithm now. And you can see here in the box on the right side, there are the parents that are chosen, and on the box on the bottom side is the offspring that is created by combining the two parents in the upper box. I speed it a little bit up for clarity. Where's my mouse? Here we go. And you can see that very slowly some individuals form on the upper side, the left upper corner, that are more red, not totally red, but more red than the others. While the rest of the population slowly begins to replace all the other individuals that aren't fit enough. You see, the green one is the last actually green, the minus 181. And it's replaced by the far more fitter examples. And you see on place 1, there's a very good rated example that is, for now, the king of the population. We can speed that up a little more. And now we see that the whole population is starting to get very, very red and very uniform in size, because that exact makeup is best fitted for the environment, because we defined a red environment is good for the circles. I have another example also with circles, but in a completely other setup. And this time we're trying actually to figure a more or less computational problem out. We have given an arbitrary playground, and it's sprinkled with some circles. And our task now is to find another circle that does not cross the playground border, that does not cross any other circle, and that has a maximum circular area. So this is our example playground. And a very good fitting solution for this problem would be this yellow circle. This yellow circle has a maximum area, but it does not cross any other border. If we now would try to implement it in a quite trivial way, we would say, okay, we check each and every position on the playground with each and every radius. And as you can see, it takes some time, and I think that's not enough time for the talk. So we need to take another approach to that. We create an evolutionary algorithm. We first have to define how an individual is made up. It has some genes, and the genes are, of course, x and y coordinates and the radius. Then we need an initial population, and the initial population is simply a number of arbitrary circles with arbitrary x and y coordinates and an arbitrary radius. We try to, of course, rate that every individual, and the fitness of one individual circle is made up by some facts. First is, does it cross the playground border? That's a penalty. Does it cross any other circle? That's a penalty. Does it? How big is the circle? And that's the rating per se. So it says how good the circle is fitted and adapted to that solution. The algorithm is quite simple. We count the overlapping circles. We count the crossings with the playground border. Then we take the area of the circle. We check if there's any outsides or overlappings, and then we take the fitness times -1, so that is actually the penalty. And if there are overlappings of fitness, we rate them even more to specify how bad that behavior is. So outside is more bad than overlapping. Then we are recombinating two circles. Then we go like this. We have two parents, the green one and the blue one, and they are recombinated into a child, and the child has, for example, here the x-coordinate of the green parent, the y-coordinate of the blue parents, and the radius of the blue parents. And when we mutate that child, it gets some points to the x-coordinate and subtracted 1 from the radius, and that is our new child. And then we are checking if this is fit enough for the population. When we put that together into an implementation, then that looks like this. We have our population of circles, and they first try to very fast get away from all the other circles because that's a penalty, and then they converge onto that free area in the midst of the other circles, meaning that they are trying to maximize their radius and to find the perfect solution. And as you can see, it goes quite fast. I'm trying this again. And it is a very far better solution than the trivial approach to that. I want to look at the characteristics of such an evolutionary algorithm. What's key is that no approach is always the same. I've 4 times the same setup and running them simultaneously, And as you can see, the approach they're taking is every time different, but in the end, they're all converging onto the same spot in the midst of all the circles, trying to maximize their circle area. Then a solution is not always deterministic. In this playground, we have 4 possible solutions because in the corners, we could everywhere find a good solution. But in that run, we found the solution in the left bottom corner. But in that run, for example, it's the right upper corner. And we run it again. Well, it's the right bottom corner. Extreme conditions are a bit hard for the evolutionary algorithm because they might not always find actually a good or a solution at all, because you see they are dancing around in the midst of the big circle and not getting anywhere productive. I want to share with you another interesting problem that's bothering CS people since ever, I'd say. We have a map, and on that map there are several cities, locations. And we have a person that travels around and wants to visit each and every position, each and every city on that map. And of course, the person wants to travel as little as possible, so it needs to find a way to it needs to find the shortest possible way. And that's, like, for example, that one. We can do this by brute force, and if we do this, we are create a nice example of this. If we're doing this, then we can actually calculate how much we would wait. We would have to wait 13 cities. That's the formula for this is a factorial of n-1 divided by 2. That's 239 million possible combinations. If we could do that 10,000 calculations every second, that would take us 6.5 hours. Again, that's too much for the talk. So we need to find a better way for that problem. So, of course, we again need to find some genes, define some genes for a possible solution, and the genes are simply the order of the cities that are visited. The initial population, again, is a combination of all cities on the map and a number of them, and very arbitrary, of course. The recombination looks like this. We have 2 parents, the green one, the blue one, and a child for this. There's an algorithm behind that that's a little complicated, but if you like and if you're interested, you can look it up in my GitHub account. I'll post a link up later on. When we're mutating that child, we simply switch 2 or more of the cities of in the route. And the fitness, guess what, is of course the length of the way, and the smaller is of course the best. And if we now implementing that, that's a fun one. Then it quite fast converges onto a good solution. It has its difficulties, but now it's nearly settled. So in comparison to the 6.5 hours we have calculated before, it's, I'd say, a little better. I've brought another problem set up. This time it's 18 cities. 18 cities would be 1.8 times 10 to the 14th possible solutions. It's 560 years to try every possible solution. And if I'm running that now, we see that very fast a good solution emerges. And to prove to you that this is not a recording and I'm just showing you a GIF, yeah, okay, that's failing a little bit. So that's a proof for you that it's not a GIF. And I'm starting again. I think we now would find a good solution that is best fitted for the problem. Okay, Murphy's law dictates that in the talk, of course, this is going to happen, that is not running on the first time. Either way, I think you got a good perspective of how this can work, how the benefits are from the problem, and that's actually it from my side. If you have any questions, talk to me. I'll be around. I'm also on the otsconf Slack channel. I'm on Twitter and have all my stuff from the talk and all the implementations on GitHub. If you have questions or find a bug, please submit an issue or a pull request. If you have some cool implementations or improvement ideas, also pull request. And I also have all the slides and all the implementations and many more cool and fun implementations up on my website, earnestly.com/evolution. Thank you very much.